Hi everyone. So in the last lecture we talked about linear regression and how to fit a line to a bunch of data points. And so what we're going to do now is expand on the subject to talk about more general types of regression. Specifically what happens if your data doesn't look like it's going to be well fit by a line. What do we do in those cases? Okay. So to remind ourselves, here is a general formulation of linear regression, right? We have some data y and we want to fit it as a function of x. And in linear regression, we're making the assumption that this function f has the form of a line. So we can write y equals some kind of slope times x plus c, which is the intercept. Now, if it's not linear, then we can assume a different form for this function. And so one thing that we can do that's really simple is assume that instead of being a linear function, we have a quadratic function. And so if you recall, a quadratic function now has one extra parameter. So I'm going to be calling these parameters p sub something. And so the quadratic function is going to be p1 squared plus p2x plus p3. Okay? So in analogy, what we'll be looking at is we have now y as a function of not just a number times x, but also a different number times x squared plus also an intercept term. So this is just a more generalized polynomial that we might be able to use to represent our data. And so the data that I'm talking about might at some point look like something like that. Okay, so if you have collected some data and you see that it has this relationship where you have your independent variable on the x-axis and your dependent variable on the y-axis, and you see that certain parts of it are positively correlated and the other parts of it are negatively correlated, you suddenly have a problem where the linear assumption does not necessarily apply. Okay, and so in this particular case, we see this interesting shape where there's actually a bowl shape, right? And so if you see data that looks like this, it might be a good candidate for trying quadratic regression on. Okay, so we're going to get to the point of how do we get to do a quadratic regression of data that may have a shape where it's either a bowl shape or it could be an upside down bowl shape, just like that. Okay, so to remind ourselves, linear regression we set up as a solution to a system of equations by writing a equation of the following form, right? So where we have a V matrix, a P, which is all of the parameters that are unknown, in which case M I'm going to call P1 and C I'm going to call P2, and I have my data points Y here. And the way that we set up the V matrix, recall from last lecture, is, as it turns out, we can list all of our X coordinates here and a column of just ones here. Here's my M, here's my C, this is my P vector, equals Y, which I'm just going to list all of my Y coordinates here. Okay, so this is how we're going to do linear regression. Now, if you notice, the functional form of the quadratic equation is actually closely related to the form of what we wrote here. So what we're going to do is build a very similar matrix to this V matrix here that accounts for the fact that we have an extra term here, which is the x squared term. Okay, so this is linear, is this version down here. And what we're going to do is note that you can write this equation, this quadratic equation here, also in matrix form in the following way. Now, so we're going to first of all look at our parameters and enumerate them. We have three unknown parameters, P1, P2, and P3. So I'm going to write them here, P1, P2, P3. And again, I'm going to have all of the Y coordinates right here. Okay, so then the only question remaining is how do we construct the V matrix here? So as you can see, if you just kind of ignore this P1 here, you look at P2 and P3, it actually looks exactly like the linear regression form, right? So we're going to actually just write exactly the same thing here. The middle column is all of the x's, and the last column are column of ones. And so P1 is actually being multiplied by all of the x's squared. So all we really have to do is take the square of all of our x coordinates and stack them up in a column here. Okay, so if you work this out by multiplying out these matrix multiplications, and you can convince yourself on your own time that this is actually true, you get to this equation. Okay, So that's what we have to do for the quadratic equation. We have to build a V matrix of this form. We have to keep track of which column is which so we know how to interpret all of these P's. And then Y actually remains the same. We just stack them up just like we did before. Okay? So let's try this out in some code. So going back here, we have our, I have just wrote a bit of code just to generate the data that we saw before. So we generate data of this type, where if we looked at it, we can convince ourselves that perhaps a linear model is not the best one to evaluate this type of data. Really, it has a higher order relationship. And let's say we wanted to try a quadratic equation instead for this data set. So what we're going to do is, just like before, construct the V matrix. But now instead of just stacking x's and 1's next to each other, we're also going to add a column of x squares right next to it. Okay? So let's do this by typing in V. And the first column is all of the x's squared, so x squared. And next to them, we're going to put a column of the x's. And next to those, we're going to put a column of 1's the same size as x. So that's our V matrix. And like before, in order to solve this equation of V times P equals Y, we already have Y. And so P is equal to V backslash Y. Okay? So let's evaluate that, and we can go back and look at the value of P that we just got by evaluating this section of the code here. Let me bring this up a little bit so that it's visible to you. Here we go. So I just ran this piece of code. I ran it again. And if we then go look at P, type in P and see what the value of P is now this matrix right here. And it has all of these parameters in that order. So it's the right size, which is always good. We double check the size. It has 3 elements like you expect. The first element is the quadratic term. The second element is the linear term. And the third element is the constant term. Okay? So this is the parameters for a parabola that we can draw. And what I'm telling you is that this is a solution for the quadratic regression of the data we were just looking at. So does it work? Well, let's try it. Let's try plotting them on top of each other and see if we've got something that looks right. So what we're going to do is we already have a plot of x versus y and points above. So now what we have to do is construct the prediction by the regression. So I'm going to make another list of x coordinates and call it y hat, and it's going to go between -5 to 5, counting by 1/100ths. This should be a 5 right here. And y hat is going to be, so if we look back on our form of the quadratic function that we want, so it's p1 times x hat squared plus p2 times x hat plus p3. So that gives us what the function is according to our quadratic regression. So if we then plot both the data points, do a hold on, and also plot our model on top of it, x hat, y hat, and let's make those a red dashed line, like so. We run that, and we see here is our quadratic regression for the data. So the data are these blue points, just like before, and on top of it we have this red dashed line that was predicted by our p vector, right? And as you can see, it actually looks pretty good. It seems to have fit the data quite well, regardless of the fact that it's kind of noisy data. And so this is a general form of building this V matrix that allows us to be able to go from data, arbitrary number of data points. So at this point, this particular example, I made 1,000 data points just for fun. But you can do this with many fewer or many more data points as you want, and build this V matrix just by thinking about the functional form of the model that you would like, figure out what your unknown parameters are and how many there are, build the system of equations like we've done here, and use the backslash command in order to solve for the parameters and come up with a fit that way.